Okay. Um, so we should now know the basic theoretical basis for K-naught conditions and where our equations for estimating K-naught come from. So we're going to start to talk now about the upper and lower limits that we discussed in the previous presentation. And there's three major earth pressure theories. There's Rankine's theory, Coulomb's theory, and the log spiral method. And we're going to talk a lot about the first two of those and just a little bit about the third, but not all today. So we're going to start with Rankine's theory because it's the simplest and easiest to understand. And I don't know where my learning objectives went for this one, so I believe they're on Blackboard. So we're going to go back to our theoretical wished-in wall here. So we have this wall that's been wished in place. So we're currently sitting here under K-naught conditions. We've magically put this rigid wall in place without changing the stresses. But now let's talk about the strength of the soil. And we're going to start with a simple, more Coulomb envelope, and we'll start with a cohesionless soil. So we have, I should have a sigma prime here. So we have a strength envelope with a constant friction angle and no cohesion. And this circle here represents our at-rest conditions. And on the right, if the ground is horizontal, like this, and there's no shear stresses that are applied on the ground, then this must be a principal plane. The horizontal plane must be a principal plane. And if the horizontal is one of the principal planes, the other principal plane has to be the vertical principal plane. So there's no shear stresses on those planes. This element, these are the principal stresses on the element. And so the major principal stress is going to be sigma prime Z0. And the minor principal stress is going to be sigma prime X0. And we should have a Moore circle for our K-naught conditions like that. I will point out there are some instances, mostly in rock, where there are really large geologic lateral stresses where you can actually have a horizontal stress that's greater than a vertical stress. And you do see that in rock under certain circumstances. But in general soils, we don't see horizontal stresses that high. So now we push the wall in again, and we're moving towards the passive condition. Right? So the passive condition was, this term passive and active, I've never really had a good, I don't know why they picked them. I like to think of the active condition as, in the active condition, the soil is actively pushing on the wall and pushing it away, and the passive condition is passively resisting the wall being pushed into it. That works for me. If it doesn't work for you, I don't know. Think of some way for you to get the active and passive conditions in your brain. So as we move, when we move into the passive condition, again, we're going to push the wall in. Our horizontal stresses, again, is going to go up, right? So what happens to our Moore circle as we go? Let's go back. Whoops. So as I go from this condition and I push the wall in, what's changing and again what's not changing? The vertical stress is constant. So the horizontal stress is going to increase. So what happens to my Moore circle? Well, it gets smaller and smaller until it becomes a point and they're equal. And I keep pushing. What happens to the horizontal stress? It keeps getting bigger and bigger. And see, the vertical stress is not changing. So how big can it get? It gets until it becomes tangent to the circle and the soil fails. And now if I push any more, my horizontal stress isn't going to increase. So this is my boundary condition. This is the maximum horizontal stress I can have for a soil that follows the simple Moore Coulomb conditions with no cohesion. Well, we'll do it with cohesion in a while. All right? Now, what happens in the case? What happens as I let my wall move away from the element of the soil. Vertical stress is again not going to change, and the horizontal stress is now going to decrease. So what happens to my Moore circle? Well, it gets bigger and bigger until, again, it's tangent to the failure envelope. And then no matter how much more I move the wall away, it can't get any lower. So I have these two limits on my earth pressure. And these are based on the strength. These are boundary, these are you hear we talk a lot about limit equilibrium analysis and limit analysis in soils. This is a case where we're doing that. These are limits based on the strength of the soil, based on our model of the strength of the soil. So I can either get the Moore circle, in the middle I'm going to have sigma prime z0, that's the vertical stress, it's not going to change. And on the high side, I can get sigma prime x max, if we want to write that. And on the low side, whoops, let me go back up. I'm not following my script. So this is sigma prime x max, and on the low side I can have sigma prime x min. Let's see, is the next one on a new slide? I don't remember. Nope. Okay, so let's look on the high side. Wait, which one of these is the passive and which one's the active condition? Is the big one the passive condition or the active condition? Right? Horizontal stress higher than the vertical stress. That's the passive. And remember when we were looking at that ratio, when we were looking at that little displacement chart before, and the difference between the passive pressure and the passive K and the active K was much bigger. Notice that your passive horizontal earth pressure is much bigger. The difference between that and your vertical stress is much bigger than on the active side. In other words, the passive circle is way bigger than the active circle. And it took more displacement to get there. You think about it. So if you're changing stresses more, it's got to take more strain to get to a bigger change in stress. So this is consistent with our observations about displacements to reach the active and passive pressure and the magnitude of the active and passive pressure. Okay, so let's calculate this. So now we know this. We know everything. We know phi prime, right? We know sigma x. We know the size of the circle. So we can calculate the ratio of sigma x to sigma z in this case, because this is all just geometry. So I'm sure it's geometry you forgot, so don't worry about it. I'll give it all to you. All right. So radius of the circle is, in terms of sigma x and sigma z, what's the radius of the circle? Yeah. Sigma x minus sigma z, that's the diameter, right? Divided by 2, that's the radius of the circle. And the distance from the origin, remember that, well, the distance from the origin is the average of the two, right? It's sigma x plus sigma z, 1/2 of that. And remember that tan phi is going to be rise over run of our circle there. We need one more thing. We need this distance from the circle origin up to the failure surface. And if you remember that tan z is rise over run, because it's the slope of the line. So if we write this, so this is the rise and this is the run. So this height is 1/2 sigma x prime plus sigma z prime times tan z. Right, everybody with me? That's the hardest thing you got to do, because the rest of it's all just it's just geometry. Okay, so notice that this interior angle here is the same as phi. That should say phi prime. And then, so cosine of phi prime is just the hypotenuse of this triangle. I'm sorry, the radius of this, the short side divided by the long side. So it's just 1/2 sigma x minus sigma z over 1/2 sigma x plus sigma z times tan phi. Boy, I missed a lot of sigma primes in here. And then this is the geometry that you forgot. But if I solve for sigma prime x over sigma prime z and do some little geometry manipulations, which I will spare you, we'll find that the sigma prime x over sigma prime z is going to be 1 minus sine phi over 1 plus sine phi, which should look familiar to you. And that means that K passive, Kp, is 1 minus sine phi over 1 plus sine phi. Now we had a lot of assumptions in here. So this is for c equal to 0. Phi's constant. And it's for a horizontal surface. Right? We also made the assumption we knew where the principal stresses were in this whole setup. So this only works for a horizontal ground surface. Because the other assumption is made. We knew that sigma x and sigma z were the principal stresses. Right? All right. So let's look at the active side. Now we're going to go look at the left side. We still have sigma z, sigma prime z still the edge of the circle, but now sigma prime x goes the other direction. It's going to be less than sigma prime z. The equations are all the same. The radius is still 1/2 sigma prime z minus 1/2 sigma, but the radius is still the difference, but now it's sigma z minus sigma x, not sigma x minus sigma z. Notice that. Remember before, that ratio was sigma x minus sigma z because x was greater than z. And now it's sigma z minus sigma x because sigma z is bigger than sigma x in this case. You with me? The distance to the origin is the same. So the hypotenuse of the small triangle in the middle is the same. And now we have that cosine theta prime, cosine of theta prime, phi prime, sorry, is now 1 minus sigma z minus sigma x. This is the only thing that's changing in our equation. These two terms have been flipped around from the passive case. That's the only thing that's changing. And so when I solve this one, I'm going to get that sigma prime x over sigma prime z is 1 minus sine phi over 1 plus sine phi instead of 1 plus sine phi over 1 minus sine phi. And that is going to be equal to Ka. Okay, everybody understand how we got here? Nothing up the sleeves. No magic. All we're using is more Coulomb failure theory for cohesionless soil, and we're assuming that we know where the principal stresses, that the principal stresses are sigma x and sigma z, so that corresponds to a horizontal ground surface. That's all we've done. All right, well, let's look at the same thing when we have cohesion. So the only difference now is that we've got both C prime and phi prime. So we'll start with the passive case. So here's my passive circle. Sigma, these still should be sigma primes. Sigma prime z on the left and sigma prime x on the right now. My radius is the same. It's still 1/2 sigma prime x minus 1/2. It's 1/2 the quantity sigma prime x minus sigma prime z. But now, when I start to build my triangles, I have this little piece on the left-hand side of my triangles. That's going to be C prime over tan phi, right? Just That's going to be that distance there. On the right, the distance to the center of the circle is still 1/2 sigma prime x plus sigma prime z. So now the height of the hypotenuse in the smaller triangle that I'm going to use in the middle, this hypotenuse is now this. It's now the sum of these two terms times tan phi. So it's c prime over tan phi prime plus 1/2 sigma prime x plus prime 1/2 the quantity sigma prime x plus sigma prime z, that entire quantity times tangent phi. Same, we're going through the same process. So we'll do the same thing. So the cosine of theta is then the the short side over the hypotenuse. So now we have this c term has appeared over here. And now when I solve for sigma prime x, it's not as neat as it was. I get that sigma prime x is sigma prime z times 1 plus sine phi over 1 minus sine phi. That's the same, right? That first term is the same as we had before. But I now have a second term that is not multiplied by sigma prime z. Notice this is a function only of c and phi. And notice what the term inside the radical is. What's this term? 1 plus sine phi over 1 minus sine phi. That's the same term as this, right? So I can now define sigma prime x as sigma prime z times kp plus 2 times c prime times the square root of kp. I'll give you a minute to write that down, and we'll have a little philosophical thing to talk about here for a moment. Now, we've always told you that k is equal to sigma prime x over sigma prime z, right? Oh. I don't know how I did that. We've always told you that k is equal to sigma prime z over sigma prime x, right? I mean, that was what we said the definition of the coefficient of lateral earth pressure was. Is that the case here? If I use this definition for kp? It's not really, I mean, this actually changes the definition of the lateral earth pressure coefficient, because it's not the ratio of the two now, right? And this is a little sleight of hand that usually in undergraduate text we just kind of breeze over and say, oh yeah, it's the square root of k. Well, so realize when we define the active and passive earth pressure, we're defining the active. We're defining we're making a very specific definition that it's really not the same as our original definition of the coefficient of lateral earth pressure. It's the one we're going to use because it works, and it's a lot better. In fact, it's better than using the definition that it's actually the ratio of the horizontal to the vertical stress, because that now changes whether you've got cohesion or not got cohesion. But realize this: we're actually doing we're pulling a fast one on you and changing the definition in the middle of the project. But this is the way we're going to do it. We're going to define this, and you're going to find out later that it's not even really the horizontal stress. So there's a lot of confusion about this. I think. Well, there's actually not enough confusion about this because there's too many people that don't understand that we've actually changed the definitions in the middle of this. But this is the way we're going to do it. We're going to define Kp in this fashion. So if you want to think about it, Kp is only the ratio of the horizontal to the vertical in the case where you have cohesionless soils and as it'll turn out later, a horizontal ground surface. Conceptually, it's still the ratio the same. It's just not quite mathematically the ratio of the two. All right. That's not what I meant to do. Okay, so let's do our little summary for the Rankine earth pressures for horizontal surfaces. So Ka, and I could do the same thing for Kp, but we're going to, Ka is equal to 1 minus sine phi over 1 plus sine phi. This is also equal to tangent of 45 plus phi over 2. You see it formed that way too. That's just a algebraic equivalence. The active force on the wall, this is our definition, by the way. This is the definition we're going to use. We're going to stick with this definition. But the total active force on the wall is going to be sigma prime z times Ka minus 2 times c times the square root of Ka. And Kp is going to be, this isn't right, this is a sigma, I'm sorry. This should be sigma prime x. I'm jumping ahead to walls, and we haven't got to walls, we're just doing earth pressure. And Kp is going to be 1 plus sine phi over 1 minus sine phi, which is also equal to tangent squared of 45 plus phi over 2. And I think this one's wrong too. This should be sigma prime x. And sigma prime x is going to be sigma prime z times Kp plus twice the cohesion times the square root of Kp. So those are our definitions. That's how we're going to define it. And if we define it that way, if we define Kp and Ka in that fashion, these are the equations. And these are the equations you'll see published in all your textbooks and the ones that are in the FHWA manuals and the sections I asked you to read. Okay, so let's talk about what that means. Let's look at the distribution of earth pressure versus depth in the active and passive case. And before to do that, let's go back just real quickly. So at the ground surface, at the ground surface, z is equal to 0, and sigma prime z is equal to 0, right? That's supposed to be a z, not an x. Let me try that again. Right? So this term at the ground surface, this term is equal to 0, and this term is equal to 0. So at the ground surface, in the active case, you have a negative earth pressure, and in the passive case, you have a positive earth pressure. These are limits now, remember, these are limits. Okay, that's probably not what we started thinking, because we normally think, oh, at the ground surface there's no vertical stress, there's no horizontal stress, everything's 0, life is good. Well, no, when you have cohesion, that's not the case. So now let's go on. So the active case, at the ground surface, I have minus 2c times tan squared of 45 plus phi over 2, or 1 minus sine phi over 1 plus sine phi. And I increase at the rate of, the slope of this line is going to be Ka. And at the base, I'm going to have gamma h times, well, the whole distance is going to be, the amount that I'm going to add there is gamma h times tan squared of 45 plus phi over 2. This term remains constant, right? And this is the amount I'm adding due to sigma prime v. Sorry, I want to. Or this amount right here is the amount that this is going to be gamma H Ka minus 2c square root of Ka. That's going to be this distance from here to here. So theoretically, in the active earth pressure, I've got negative earth pressures for some distance from the ground surface when I have cohesion. And on the passive side, I'm going to start out at the ground surface with a positive 2c times tan 45 plus v over 2. And I'm going to add the same, this is still going to increase at the rate of Ka. And I'm going to add another gamma H tan squared 45 plus v over 2. So the entire length of this at the base is again going to be gamma H times gamma H times Ka, in this case plus 2c square root of Ka. I'm sorry, Kp. These are p's. And this is increasing at the rate of Kp, sorry. So if I draw that to scale, this line should be much, much steeper, something like that. So in the passive case, before I do, at the ground surface, I've got a positive earth pressure on the soil, even for no vertical stress, because of the cohesion. How are we doing? We're doing okay. Just looking ahead to see how many we got. All right. Well, we'll see how far we get with this. All right, so far I've basically talked about effective stress conditions with no pore water pressure. So let's talk for a minute about, and that's easy to do. All we got to, if there's pore water pressure, we're just going to subtract the pore water pressure, and all that stuff we've done is fine. So let's not worry about that. And we'll talk about some of the implications of that later. But so to this point, mathematically, everything's dependent just on a more Coulomb failure criteria and more circles. So it should work fine, and I did it with cohesion and without cohesion, so it should work fine for the case where phi equals 0. It's just that, phi is going to be equal to 0. So we should be able to do it with total stresses. So our effective stresses, again, this is our shear strength. It's just equal to C prime plus sigma prime tan phi. We're going to compute the lateral earth pressure using effective stresses, and then if there are pore pressures, we just add those in as pore pressures. So under effective stress conditions, we're just going to take, we take the pore pressure away, calculate our lateral earth pressures, and then going to put the pore pressure back in at the end. Another way to think about that is, what's the lateral earth pressure, what's the active pressure for water? 1. What's the passive earth pressure for water? 1, right? Water has no shear strength, so it's got, and so if you want to think about it, what we're going to do is we're going to take the water out of the equation, we're going to calculate the lateral earth pressure for soils, and then we're going to calculate the lateral earth pressure for water and put it back into the soil. But we got to do them separately, right? We got to calculate the stresses and the forces due to the earth separately from those due to the water and add them together to get the total horizontal stress. For total stress conditions, we just have that phi is equal to 0, right? Mathematically, everything else applies. So all we're going to do is we're going to use the same equation. The math doesn't care, right? The math does not care why phi is equal to 0. We just did this all with math. Math doesn't know squat about soils. So it should work fine. We're just going to use phi is equal to 0. Our cohesion is now equal to the undrained shear strength, SU. And then Ka is equal to Kp is equal to 1, because 1 minus sine phi is 1 minus 0 over 1 plus sine phi is 1 plus 0. And the inverse of that, so that's 1 over 1. And the inverse of that is 1. Which is why the lateral coefficient of earth pressure for water is also equal to 0, because it has no friction. In that case, sigma x is equal to sigma z plus 2 times the undrained shear strength. Or I should say, I did that too fast. Plus or minus, right? In the active case, it's going to be minus, and in the passive case, it's going to be plus. All right. So there's a couple important implications of this. One thing that everybody knows that if we go by someplace that's clay, you go out to the dry lake beds, and you see cracks in the ground. Why do you see cracks in the ground? Because they're cohesive soils, and they stand up with no lateral or earth pressure. In fact, you can go some places, and those things are really, really deep. I mean, people can stand in them if they were wide enough. You can certainly take a meter stick and stick them way down those things. So we know this happens, right? Well, those are called tension cracks. And so if we look at phi equals 0 conditions, if we look at the active, and that's an active case, right? When you got a crack, the wall, in this case the wall is more soil, but it's moving away from the other one, so that's unloading, so it's an active case, right? So under phi equals 0 conditions, we already said that this was our lateral earth pressure diagram, right? It starts off negative. This is on the if this is sigma x, I'm plotting here, and this is the negative side, and this is the positive side. That's minus 2 SU at the surface, and it increases at the rate of 1 times sigma prime, not sigma prime, sigma z, right? Because so the total, so sigma prime x is equal to sigma prime z minus 2c, which is just gamma z minus 2 times SU. The total horizontal active earth force then is just the integral of, this is sigma x here, right? The integral of sigma x dz from 0 to whatever height I want to get to. And at some height hc here, this thing is going to be equal to 0. Because right on the top, I've got a force acting to the left, and on the bottom, I've got a force acting to the right. So for this case, where phi is equal to 0, this is just equal to 1/2 gamma h squared minus 2c. And if we want that to be equal to 0, I just set that equal to 0, and I solve for what I'm going to call the critical height, and it's 4 SU divided by gamma. Now we got a statics problem in there, right? What are my structures, guys? What's our statics problem there? I did summation of horizontal forces equal to 0, right? But what's my statics problem? If this is actually my free body diagram, and I've got one force here and one force there, and they're equal, what's happening to the soil? It's spinning round and round and round. I got a moment. So, we're just geotechnical engineers. We ignore simple little things like that, trivial structural issues. After all, the world spins, Earth spins around and around, right? So this is the theoretical height for an unsupported vertical cut is theoretically 4 over SU. The depth of the tension crack, in other words, the depth where you have negative stresses, is half of that, or 2 times SU over gamma. And so the unsupported height is someplace between those two, you know, if you want to think about it. The unsupported height that you could theoretically cut for undrained conditions, so this is a short-term condition, right? It'll eventually go away because we're under phi equals 0 conditions, was a short-term condition. There's someplace between 2 and 4 times SU over gamma. This becomes important in the slope stability analysis and things where you get tension cracks forming at the surface, and you got places where you assume that what you usually assume then is if you have a tension crack, you assume that the actual stress from in this zone is actually 0, not negative. And we generally like to, in walls, assume that the soil isn't actually going to suck the wall back and hold it up. So in those places where we get negative stresses, and generally we will generally consider there to be 0 stress there instead of a negative stress. Because we all know that soils don't suck. We wouldn't be geotechnical engineers if they sucked. Tough crowd. I got one guy smiling. Man, you guys need to get to know me better. All right. Let's go through this section and see how far we get through this section. I've got a couple more stopping points in here we could stop at. Let's locate the shear surface that we get in Rankine theory, because this is going to be important to us. So here's my element of soil, again, behind my idealized wall, and someplace, realize that when in Rankine theory, what we did is when we let the active condition, we let the wall move away, we let it move away until we reach a state of failure, right? You remember the slide. In the active case, we let the wall move away until it reaches failure, and in the passive case, we did the same thing. We let the wall, we pushed into the wall until it reached failure. So behind the wall, in either case, the soil is in a state of failure theoretically in this. So we can use that observation. We can use that observation to locate where the failure surface is. So that's what we're going to do now. So if we can determine the orientations of the shear planes of the failure planes, then we can locate where the failure surfaces are. So here's my here's my 2 more circles, the passive circle and the active circle. So let's start with the passive case. So the passive case, remember that sigma prime x is greater than sigma prime z. This is the pole point of my circle, right? This is the plane. You know, what plane do the x stresses act on? The x stresses act on a vertical surface. So the pole point is I'm gonna draw a line from here through the point, the line from the location where the stresses act parallel to the plane on which they act. That's going to be a vertical plane. And where does that intersect the circle? At the tangent. Or if I start over here, the z stresses act on a horizontal plane, right? So if I draw a horizontal line through here, it's going to intersect the circle at the pole point. So that's my pole point. So there's my pole. These are the failure planes, right? Here's my failure planes. This is the failure point. So this has to be the failure planes, and the 2 failure planes are at 45 minus phi over 2. So that's just geometry. I'm not going to do the geometry for you. And on the active side, sigma x is less than sigma z. My pole point is now on the other side of the circle, right? And these are my failure points, and my failure surfaces are at 45 plus phi over 2. So these are my failure planes. And in the passive case, they're at 45 minus phi over 2, and in the active case, they're at 45 plus phi over 2. See, you guys from 531 thought we were never going to talk about pull points again, did you? Okay, so let's talk about where they are. So the location of the surface. Well, in the passive case, my failure surfaces are located at 45. There's a conjugate pair, right? There's a pair of failure surfaces. My failure surfaces are located at 45 minus phi over 2. So this whole area in the passive case is under failure. So if I want to know how far back I need to go from my wall to get away from where the failure surface is, I can calculate that distance based on knowing h and the angle there, right? And for the active case, that's not what I wanted to do. On the active case, my failure surfaces are at 45 plus phi over 2, and the two conjugate pair of failure surfaces look like that. And this is, we want to call that XA. This is the height. Right, this angle here is then actually going to be 45 minus phi over 2, right? And tan of 45 minus phi over 2 is going to be equal to opposite over adjacent x active over h, or x active is going to be h over tangent of 45 minus phi over 2. And the passive we could have done was going to be h over tan of 45 plus phi over 2. That's pretty sloppy. That's going to be important, for instance, when we decide to design a wall that has an anchor. If we're going to put a dead man anchor here and put a tie rod in to tie our wall, we probably want it behind the active surface. It's not going to do us a lot of good to come in here and put our dead man right here and tie it in, because it's not going to be doing much anchoring, because it's just going to be moving with the wall. Woo! Got excited. Right? Let's see if I broke this. Oh, good. All right. Let's see. Yeah, go ahead. I think so. This is tangent of this angle is opposite over adjacent, right? Oh, yeah. I don't know. I just did that on the fly. It's always a good thing to ask, because I screw this up a lot. Did I do that right? You guys tell me. Watch it in the video and come back and tell me if I did it right next week. How about that? That'll get you watching the video. I'm pretty sure that's right. Let's see. I don't think if I start this next section we're going to get done with it, but let me look real quick at where we're at. Let me decide if I really want to do it fast. I think we can do it. Besides, I don't think you want to come back to this. All right, so that was nice, but everything we've done so far, so now we've come quite a long ways. We've talked about active and passive pressures for cohesive, purely cohesive soils, in other words, for phi equals 0 conditions, for cohesionless soils, and for both, and for the in-between case. But they've all been for the horizontal surface. So now, what if the ground surface isn't horizontal? All right, and so we're going to call the slope of the ground surface beta. Now the elemental element we're going to use is this little parallelogram thing, which is a little weird, but there's a reason we're going to do that. We're going to call the center of that z, and we'll call the width of it dx and the height of it dz. But it's not a square right now, so this is a little strange. But there's a reason we're doing this, and we'll just call the thickness of that thing in the middle pt. And we're going to call the distance along the other side. I'm sorry. We're going to call this is not the thickness. This is a force. This is a force. The force acting on the top, PT, and the force acting parallel to the ground surface, we're going to call that PV. I don't know why I did that, but I guess we'll find out in a second. I'm actually call these stresses. I'm sorry. So PT is the stress on the top plane. I know why I did this. And PV is the stress on the vertical plane. So those are stresses, not forces. So let me get rid of that. And one of the reasons we do this is, I'll show you why we do this. Here we go. So, the PV must be parallel to the vertical plane. And we're going to sum forces in the z direction equal to 0. So gamma z times dz, right? The stress at this point is still going to be equal to, this stress is still going to be equal to gamma z, right? Because it's still a vertical stress, right? So gamma z times dx is got to be equal to, it's not, gamma z is a vertical stress, it's not PT, it's not the total force on the surface. It's equal to PT times dx divided by cosine beta, because that's the length of that. And then, so we can just write the PT is equal to gamma z times cosine beta. Whoops, going too fast for you. So all I'm doing is taking this stress on this plane and making it the stress on this angled plane. That's all I'm doing here. Okay, so now let's look at, and we do that because let me back up again. The reason we're going to use this plane is because what are the shear stresses on the ground surface? 0. Right? So the shear stresses on this surface have to be 0 too. So we still got our Mohr circle. We still have our Mohr Coulomb diagram. If this is this is beta, so that's the angle on which that's the point where PT is acting at point A. We're going to draw our Mohr circle in. There's some shear stresses on that, but we're going to know this point because we know this direction, right? Because this is remember, I'm going to draw the circle like this, so this is the stress acting in that direction. This is the stress acting in that direction. So this has to be the pole point. And then from there, I can calculate that PV has got to be this value. And I can draw this little triangle in here. And then what I'm trying to find is PT over PV. So from O to C, EC, which is this distance, is going to be OC times sine of phi. BC, from here to here, has got to be OC. I'm working on this triangle in there times sine of beta. And so EB from here to here has got to be the square root of those two. The square root of the sum of the square root of the difference of those two. Or I can write that EB, the height of this triangle right here, is a square root of OC squared sine squared phi minus OC squared sine squared beta. That's all nice. Or what I was looking for in the whole thing was this distance from here to here, OB, which is just going to be OC times cosine beta. So now I know all these elements of those two triangles, which is what I need to do to calculate my stresses. Okay, so PV, which is the stress at that point, is got to be OB minus EB. So that's OC minus cosine beta minus the square root of OC squared sine squared phi minus OC sine squared beta. Sorry, going too fast. There it is. There it is again. I ran out of room, so I have to rewrite it. And PT, which is the total the stress at on the top, has got to be OB plus EB. So that's OC cosine beta plus the square root of OC squared sine squared phi minus OC squared sine squared beta. And then I can write the ratio of these two as cosine beta minus sine squared phi minus sine squared beta over cosine beta plus sine phi over sine squared beta. So what I've done now is I've defined, remember that I was defining this stress P top, PT, which was on the top, versus this PV on the vertical face, and they're not normal to each other anymore. But this is what we're going to define as, in this case we were doing the passive, right? Yeah. We're doing the passive? I think so. Let's see, minus, no, this is the active case, right? Because it's smaller on the top than the bottom. Let's see, beta minus, yeah. So this is PV over PT, but PT is, I got ahead of myself on the previous slide. I don't want to say this yet. But PT is sigma V times cosine beta. Remember, PV was based on the angle and not the horizontal surface. So then I can write that PV over sigma prime V is going to be cosine beta times this whole quantity that we just derived, and that is going to be equal to Ka. And Kp is going to be similar. We're just going to switch these signs because we're going to be working on the circle on the other side. And that you should recognize as the Rankine earth pressure for the case where you have a sloping surface. So I'll give you a minute to copy that down, and then we'll go to our concluding slide. I think there's just one left. Yeah, one and then a summary slide. And when it's beta, and beta is equal to 0 for horizontal surface, this turns into 1 minus sine phi over 1 plus sine phi, and 1 plus sine phi over 1 minus sine phi, right? When beta is equal to 0, this goes to 1, this goes to 1, this goes to 1, this goes to 0, this goes to 0, and you just get 1 minus sine phi over 1 plus sine phi, which is good, because that's the case we got for the horizontal surface, right? All right, so give me 2 more minutes. I'm not going to derive this part, but you can also derive the, I'm not going to go through this part, I'll just leave it in the slides for you. You can also figure out where the failure surfaces are, just like we did before. And you get 2 different angles in this case, I and J. And these are for the active case, those are the values of I and J. And for the passive case, those are the values of I and J. I'm not going to derive those ones for you. Okay, so here's our summary. I'm just going to go right through this whole thing. So here's our summary. for the Rankine earth pressure. And by the way, I'll give you a handout that has all the equations, the final equations for Rankine, for both Rankine and Coulomb together. So our assumptions are the soil, we didn't actually go through this in the beginning, so let's go through it now. The soil is homogeneous and isotropic. The more Coulomb failure applies, and the soil behind the wall has to be able to get into a general state of failure. And it has to, technically, it has to encompass that zone that we computed that was within failure. So what are the implications for us? Well, the failure surface is planar. That's just an assumption that comes from, really, that comes out of the Moore Coulomb criteria. The failure surface is planar. The resultant earth pressure acts parallel to the ground surface. And the wall has to displace to reach these. Am I at the end, or do I have one more? I'm going to stop and finish these because I'm over already, and I don't want to go over 10 minutes. I'll put these last two in the lecture capture just so you can look at them. We'll come back real quickly and cover them. This one discusses how we deal with earth pressures in layered systems, and I'll come back. It's just an approximation we use, and I'll come back and talk about that. I just wanted to be in the lecture. And then this just summarizes all the equations. And the important thing to understand about this one is, technically, when we calculate, the coefficient of earth pressure here is not a coefficient of lateral earth pressure, it's a coefficient of the resultant earth pressure. Because remember, when we did this derivation here, we were comparing the vertical stress to the stress on this vertical surface and the angle of this was parallel to the ground surface. So our definitions, when we use this equation, our definitions are not for a horizontal surface. This definition is the same. This equation still applies down here, except that PA is not horizontal, it's parallel to the ground surface. There's a lot of confusion in that. Some people assume that if you multiply the vertical stress times Kp, that you're always going to get the horizontal stress, but not the way we defined it. It's the active earth pressure coefficient for Coulomb, and it's going to be the same for Rankine, it's going to be the same for Coulomb, is defined as the ratio of the vertical stress to the resultant earth pressure, and it's only horizontal when the ground surface is horizontal. Okay? So I'll come back and go over these at the beginning of the next lesson, but I wanted them all to be in one webcast. And that must mean it's time to quit. Is that what it means to me? All right, I agree with you.